All right. Welcome to my talk. I have the honor of having the talk right after lunch, where you are still chewing your pizza. And I'm sorry to distract you from this. Yeah, but my hope is to make it through before the sugar spike kicks in so that you can still listen. The other strategy to attract your attention, I decided to choose this great title, Implication as Algorithmic Containment. Tantalizing, isn't it? And so I want to talk to you about reasoning. We have two major approaches, like in neural nets and like sub-symbolic reasoning and symbolic reasoning. Well, neural nets often are quite bad at it because there's a lot of hallucination or confabulation in LLMs. And if you think about how people reason, if I show you this bottle and ask you, well, if I open it and tip it and you know there's water in it, you're gonna assume the water will flow out. So how do you do that? It appears like you imagine this bottle, even if you don't see it, and play this video in your mind. And then you see that water flows out and you do perception on your imagined picture. And in this perceptual process, you extract the property that water is then on the ground. So this is what I mean by grounded reasoning. And I would like to suggest a third alternative. So apart from the way it's done in neural nets, and also not in the way it's done in symbolic systems. So in symbolic systems, what is a symbol actually? Right? What is a symbol dog? How does it relate to a real dog or the image of a dog? Well, I don't really know how, apart from the letters dog being acute in the human mind that remind us what a dog is. So it's basically cues a representation of the human mind. Essentially, a symbol is so the meaning of the symbol is actually extrinsic to the AI. It's outside of the computer. It's inside the human mind. So for the AI, you could actually replace the symbol by any other symbol. And that notion is expressed by Harnett in the famous symbol grounding problem. How can the semantic interpretation of a formal symbol system be made intrinsic to the system rather than just parasitic on the meanings of in our heads? How can the meanings of a meaningless symbol tokens manipulated solely on the basis of their arbitrary shapes be grounded in anything but other meaningless symbols? So I want to argue that symbols are not really representations because they do not contain any information about what they represent. What do I mean by that? Well, the alternative, a representation of an image of a dog, would be a bit string where the image of a dog is also a bit string underneath. And when one bit string has information about another bit string, what do we mean by that? Well, it means that there is a relatively short program, like a Turing machine, that takes the representation and computes what it represents in an easier way than without the representation. So in the language of algorithmic information theory, the Kolmogorov complexity, oops, what did I do there? The Kolmogorov complexity, which is the shortest program computing X from R, would be shorter than the Kolmogorov complexity of X, so the shortest program computing X. So in some sense, a representation has to be somehow helpful in computing that thing that it represents. So what can we do with this? Symbolic versus grounded reasoning here. The other problem that symbolic reasoning has is this combinatorial explosion. If you want to make, if you have a rule from A follows B, from B follows C, from C follows D, there are all sorts of other distracting rules that you may want to, you have to traverse in order to find D. So you have a combinatorial explosion. What I rather want to suggest is if you have a generative model A, So properties should be generative models or world models. Then you can just sample from it an instance of what you want to represent. In this example, an equilateral triangle, and then you do perception on that instance, and you perceive the consequence and derive the implication. So how could this might work? How can we be sure that this is always true or something like that? So in the formalization here, F would be the premise, P the parameter, everything else about this triangle, like its position, its size, its orientation, and X is just a particular instance of the triangle. And we just search, for example, if you want to search for another properties, like in the statement, every equilateral triangle is an isosceles triangle, G would be the isosceles triangle that we would like, and we derive that property from this instance. So how might this work? So first of all, I would like to show you how in my system that I've been developing over the last year called William, it's a data compression system based on program synthesis. So in this example, you give a triangle example of an equilateral triangle, like a list of coordinates of 3 lines, and then it discovers point 1, 2, 3, and then it discovers a difference vector, and every step it compresses the data. And then it discovers, transfers the difference vector in polar coordinates, and then it discovers that the lengths are equal, 2 of the lengths of the triangle are equal, and then finally it discovers that all angles are equal to 60 degrees. And that compression process basically it discovers this property of equilateralness. And the same thing you can do with the isosceles triangle, where basically the same properties are discovered here, except for that the angles are all equal. So you have just two sides of equal lengths. That is what this discovers. And you can notice from the shape of the graph that it's discovered that the description of the isosceles triangle is already kind of very similar of the equilateral one. And that gives you a hint that one is implied by the other. Let's move to the main theorem here. What do I mean by algorithmic containment then? Algorithmic containment of the string G in the string F means that there's a short program computing G from F. So here in this question, in this example, you can take the F is 0, 1, 0, 0, 0, 1, and G is just a flipped version of it, 1, 0, 1, 1, 0. And there's a short program computing one from the other. And that is what algorithmic containment means. In our context, it means that we don't really have to write down the consequence of our rule. If we have a premise, we can start discovering the consequences from the premise because we can compute them from the premise by using this process. That's what implication actually originally means in the colloquial sense. From etymologically, implication derives from Latin implicare, which is involve, entangle, or to fold in. So it's there without being explicitly stated. My suggestion is that we come back to that original meaning. And in terms of the theorem, if you have a feature, which is a property that compresses your data X, this is a Turing machine, takes some parameters P, and if you have another feature G that is contained in X, that is true for all as I show in my theory of incremental compression, all features are contained in the instance. Like my body size is contained in the image of me, for example, because you can compute my body size by taking an image, a picture of me. And additionally, if the parameter does not contain if you don't smuggle any information in the parameter about the consequent G that you want to conclude, then you can actually follow that your consequence is contained in the premise. And how does it work? Like schematically, if you have split the information inside your sample into F and P, that happens automatically when you do incremental compression. The information inside X is split into two pieces and that do not overlap. And if P and G do not overlap as well, then and G is also contained in X. So the green information has to be contained in the black box, but it cannot overlap with P. Well, then it must be contained in F. That's a graphical representation of how the theorem works. And we can see that how it can work also in practice. What happened to my slides? Oh, okay. All right. What we have established now is that for some particular instance, we have this implication. But ideally, right, if you want to really replace the implication rule, we would have to show it that's for all instances is true. Well, here we can just do a simple thing. We just sample. If you want to know that every equilateral triangle is also isosceles, you just keep sampling several random equilateral triangles, discover the same thing about them, and then you can show that the fraction of cases where this is true converges to 1 with this speed. So it converges to 1 exponentially if you pick a couple of really non-random samples. So if you don't, if you just sample random parameters, random equilateral triangle, you will cover the majority of the space. It doesn't guarantee you that there are no exceptions, but you cover a large parts of the space. And here's how it works in my system, William. Here's the graph for the equilateral triangle. Here's the one for the isosceles. And you sample a parameter, and then, oh, there should be an animation. Okay. There should be values propagating from here to there, and this should be inverted here. So basically, the system discovers or verifies the isosceles property. If you do it vice versa, if you have here an isosceles triangle and here an equilateral, it will fail here at the last point where it discovers usually that all angles are equal. Well, in this case, they won't be equal, so the propagation fails. That's how the system actually verifies the statement. So, and another cool thing about it, the question is, how do we discover what actually follows from our premise, right? Since we don't have it given. Well, if you have an isosceles triangle here and drop a perpendicular on its base, you discover, it cuts the base in two. Well, that's not a random thing. If you take a random split at the random position, it's not going to be split in half. So you have here a non-random property. In the terms of algorithmic information, you will be able to compress the data a little bit. And that amount of compression, here the average number of bits that you can compress the data with, means that the number of samples you need to test your implication is going to be lower. The better you compress, the fewer samples you need to test your implication. So that you can just use compression criteria to come up with implication statements that are likely to be true. So now the important question, well, what if there are rare examples? Well, for example, Um, 3 points form a triangle. Well, unless they are collinear. Or 2 random lines intersect unless they're parallel. Or 2 circles intersect in 0 or 2 points, well, unless they're tangent to each other. So do you notice that the exception has always somehow some regularity to it, right? So the distance equality or equal slope or collinearity. Regularity means compressibility. So you actually, there's the hypothesis, well, maybe in many cases, exceptions have a compressible structure. So by looking for compressible properties, you can actually find exceptions to your conjecture. And there's also a theorem to it. I'm running out of time. I'm afraid I'm not going to go into it. But here is an example with system William again. Let's test the statement that all angles in a triangle are smaller than 179 degrees. Well, if you sample triangles randomly, most of the time you won't discover an exception to that rule. So random sampling requires 116 samples to discover a contradiction. But if you sample the triangle points, the coordinates, in a simplicity biased way, that means instead of picking random numbers like here, you simple numbers here, where, for example, all 3 x values are 0. That is a simple thing. You don't need much description because all 3 x values are the same. Your description length is lower. Well, what you have discovered, well, if all x values are 0, they're all on the line. It's a collinear. These are collinear points, so it's a degenerate triangle, and exactly the case where the statement fails. So even in this example, in the first sample, it disproves. So I summarize, how should we do grounded reasoning? How do I suggest to do it? Discover properties by compressing data. Then connect those properties by sampling. Just take one property, make some samples, discover subsequent properties, and make several samples to test it. If your consequent properties compresses data well, you need fewer samples to test it. It's a big hint that the implication might actually be true. And challenge in the end your implication by simplicity bias search for exceptions. And then it's, of course, you cannot never be sure that you have really 100% certainty of that the implication is true. It's not a panacea. Exceptions are not always simple and are not always even computable. But let's remind ourselves, why do we want 100% certainty? It's because we do chaining. We want, in formal logic, we want to chain one rule after the other. And if we have even a small uncertainty, the error will multiply during the chaining. So, and you get that problem where? Exactly in the non-empirical disciplines like math and philosophy, where you're not allowed to look at the world. But for working AI systems, we are allowed to look at the world. We can say, we don't need chaining, we just directly sample our hypotheses and test them. So we can afford to be wrong 1% of the time. So good compression is also not the same as semantic clarity. That's also a drawback. It doesn't mean that it's completely clearly interpretable what you get if you have a program that compresses things. But in a symbolic logic system, you have no connection a priori between the symbol and what it represents. So just because you write down a symbol that has clear semantic clarity for you, you still haven't connected it to the world. So all the work is still ahead of you. What about complex concepts, not just Euclidean geometry or abstract concepts? Well, these are difficult things. What grounded reasoning, it doesn't give you the solution for that. But what it does, it forces you to actually connect your reasoning system with the world. And sometimes if the world is complex, you have to have complex models that represent it. But that's what reasoning requires if you really want to reason about the world. So, okay. Yeah, I think I'm basically done. I think where the AI is moving now toward world models actually is a good direction. And if we really add compression criteria to them, that could help us make great advances in reasoning. Thank you for your attention.